Right. So last class we discussed different arrangement of resistors to find out effective resistance. We used we discussed the concept of symmetric resistance networks also. Okay, fine. So today we'll discuss about Wheatstone bridge. Okay, that is a specific arrangement of resistors, 5 resistors actually, in which no two are in series and no two will be in parallel also. If any of you are very comfortable with Wheatstone bridge, how you, if you know what is balanced, unbalanced, how to find out effective resistance in case of balanced and also in case of unbalanced, then you need not attend this class. Okay, so consider this set of resistors. For now, we are only taking 4 resistors. Okay, R1, R2 on the left side, R3, R4 on the right side. Now you can clearly see that R1 and R3 are in series, R2, R4 are in series. Let's say this combination is connected to a battery. We are still dealing with ideal cells only. Okay, so let's say its EMF is V. When you close the switch, we know current will flow, and current flows like this. Since there's only one battery, no other source of EMF in the network, uh, current will flow out of the positive terminal. It enters into this junction and it splits along these two paths. Some current goes in the upper path and some current goes in the lower path. Let's call the current going that way as I1 and the current going this way as I2. Total current is I. Okay. One of you quickly tell me, in terms of the currents and resistances, what is the potential difference across this resistor? How much is the potential difference across R1?
I1 R1.
I1 R1. Correct. How much is the potential difference across R2? Directly you can tell V is equal to IR, I2 R2. Okay, fine. Now, assume V is known, R1, R2, R3, R4 are known. Okay, so we know the voltage and the resistances. How much is the current I1? In terms of voltage V and the resistances, how much is the current I1?
V by R1 plus R3.
Okay. See, the battery is connected between this point and this point, right? So if you want to find out the current flowing in the upper branch, we know the total potential difference across the upper branch is V. Okay, so for R1, R3 combined, the total potential difference is V, and R1, R3 are in series. Effective resistance is R1 plus R3. So the current I1 becomes V divided by R1 plus R3. And similarly, you can tell I2 is equal to the same voltage V divided by R2 plus R4. Okay. Now, potential difference across the first resistor R1 is I1 R1, and I1 is V divided by R1 plus R3. So we can write potential difference across the first resistance as V by R1 plus R3 into R1. So V R1 by R1 plus R3. This can also be written as V divided by, send that numerator R1 to the denominator, it becomes 1 plus R3 by R1. Similarly, potential difference across R2, I2 R2, that becomes, I2 is V by R2 plus R4, multiply that with R2. So it becomes V R2 by R2 plus R4. Okay. This can be written like send R2 to the denominator. You can write this as V divided by 1 plus R4 by R2. Okay. So what we have derived so far is potential difference across R1 and potential difference across R2. Now tell me, like you can see the expressions for both of them. When will these two be equal? Potential difference across R1 should be equal to potential difference across R2. When will that happen?
R3 by R1 is equal to R4 by R.
Correct. This part should be equal to this part. Then left hand side will be equal to right hand side. So they'll be equal when R3 by R1 is equal to R4 by R2. Or you can even interchange them and write R1 by R2 should be equal to R3 by R4. Okay. What if they are equal? Now see, if the potential difference across R1 is same as the potential difference across R2, R1, R2, they have their left terminal in common. Let's call the potential here as V1. If the difference across R1 is same as the difference across R2, then this point and this point, let's name these points as X and Y. The point X and the point Y, if the differences across R1 and R2 are same, then Vx will be equal to Vy. Okay, this is Vx, this is Vy, and those two potentials will become equal. So you can say that when the ratio of resistors on the left hand side is equal to the ratio of resistors on the right hand side, we can say that potential at X becomes equal to potential at Y. What if the potentials are equal? If the potentials at X and Y are equal, then even if you connect an extra resistance between them, the fifth resistance, there is not going to be any current in it. Why? Because the fifth resistance, that resistor doesn't have a potential difference. Why will there be a current? Okay. So in that case, current in the fifth resistor becomes 0. And when a resistor does not have any current passing through it, you can remove the resistor altogether. The circuit will behave in the same manner. That is one thing you can do. When a resistor doesn't have a current passing through it at all, you can remove the resistor from the circuit. It will not disturb the circuit in any manner. Okay. One more thing you can do is you can replace the resistor with a wire also. Because X and Y now are at the same potential. 2 points at same potential can always be connected with a wire. It won't disturb the circuit. Okay. Now, why should we remove the fifth resistor or replace it with a wire? Why do we even bother about such things? Because you consider this resistance network only. There are 5 resistors here. Okay, you all look at the resistors and tell me, are any 2 resistors in series or in parallel out of these 5 resistors? Are any 2 resistors in series or parallel?
No.
They will not be. Okay. And in this case, there is no symmetry also. There's no guarantee of symmetry, right? Like if at all you want to find out, I mean, you want to draw a line of symmetry, it will be like this. But what's the guarantee that R1 is same as R3 or R2 is same as R4? There's no such guarantee, right? So there may not be a symmetry in this case. So how do you find out effective resistance of this network? So one thing you can check is the ratio of resistors on the left side, R1 to R2. Check if it is equal to the ratio of resistors on the right side. If that ratio is equal, if R1 by R2 is equal to R3 by R4, what can we say? That current in the fifth resistance will be 0. And if current in the fifth resistance is 0, it means the fifth resistor doesn't matter. So what if it doesn't matter? If it doesn't matter, like here, if the ratio R1 by R2 is equal to R3 by R4, R5 can be ignored. What if we ignore the fifth resistance? If we ignore it, it's actually the reverse of how we derived now. If we ignore the fifth resistance, then you will see that these two are in series, these two are in series, and that series is in parallel with this series. You can find out the effective resistance. You can do one more thing also. Ignoring the fifth resistance means, like we proved that potential at X will be equal to potential at Y. So I said there is another way also of ignoring. You can connect it with a wire. Once you do that, you will see that R1 is in parallel with R2. Find out the effective resistance. R3 is in parallel with R4. Find out the effective resistance. And this parallel combination is in series with that parallel combination. You can find out the overall resistance. Whichever way you do, you will get the same answer. So there are two possible things that you can do. But when is this possible? Only when the ratio of resistances on the left side is equal to the ratio of resistances on the right side. Okay. So an arrangement like this, an arrangement of 5 resistors, not just resistors, you can have a similar arrangement of capacitors also. I told you in the last chapter itself that we will discuss Wheatstone bridge when we discuss resistors. So you can have 5 capacitors also arranged like this. So an arrangement of 5 capacitors or resistors in which no two are in series or in parallel. This arrangement is what we call a Wheatstone bridge. And if this condition is satisfied, if the ratio of resistances on the left side is equal to the ratio of resistance on the right side, we say that the bridge is balanced. Okay. The Wheatstone bridge is said to be balanced. Now don't get misled by this word balanced. Balanced doesn't mean the resistance on the left side should be equal to the resistance. The resistance as such need not be equal. The ratio of resistance has to be equal. Okay, then you say that the Wheatstone bridge is balanced. And when it is balanced, what can we do? We can ignore the fifth resistor that is there in between and find out the effective resistance of the network. Okay, let's quickly solve two problems based on this. Just check if the Wheatstone bridge is balanced or not, and then tell me the effective resistance. Calculate effective resistance between A and B. Isha, what do you say? Is the Wheatstone bridge balanced or not?
Yes, sir. The first one is balanced.
Second one is not balanced.
Yes, the second one is also
Okay. First one, what is the effective resistance?
16/3.
Okay, fine. All three of you gave the same answer. Okay. Quickly calculate resistance in the second case, all of you. Okay. Second one is also balanced. Ratio is 5/2. 10/4 is also 5/2. The 1 ohm can be ignored. Upper side 5 plus 10, 15. Lower side 2 plus 4, 6. Okay. 15, 6 in parallel becomes 15 into 6 by 15 plus 6. 15 into 6 is 90. 15 plus 6 is 21. 3 sevens, 3 30s. 30 by 7 ohms is the effective resistance. Okay. Even if you replace the middle resistor with a wire and take 5 2 to be in parallel, 10 4 to be in parallel, and then them to be in series, you will get the same answer. Okay. Now see, there are different ways of drawing a Wheatstone bridge. How you identify it is that there should be 5 elements, no 2 in series, no 2 in parallel. This is also a common arrangement. I'm sure you all must have seen this. Assume each resistance is R. Tell me the effective resistance. First, is this a Wheatstone bridge or not? You check carefully, you will notice that there are no 2 resistors in series, no 2 resistors in parallel. Totally, there are 5. So it has to be a Wheatstone bridge. There is no other possibility also. Okay, if you want, you try to draw a network of 5 resistors, no series, no parallel, not a Wheatstone bridge. You can't. Okay, try to draw it like that if you want. You'll understand whether it's possible or not. Okay. Now, how is this a Wheatstone bridge? Like, it doesn't look like this. It doesn't look like the diagrams we considered earlier. Now you see, to the point A, there are the ends of 2 resistors connected. To the point B also, there are the ends of 2 resistors connected. Okay. Where are the other ends of those resistors connected? From one, it is connected here. From this also, it is connected here. Then another one. Those two are connected here. And see, as I said, it doesn't matter whether you take the point B here or here. And same A could be here, it could even be here. Doesn't matter. So it's just a matter of visualization. Yeah, you can take it somewhat like this. Pull A to the right side, pull B to the left side. Then what will happen? These two will become the left side resistors. These two will become the right side resistors, and this will become the middle resistor. And ratio on the left side is R is to R1. Ratio on the right side is R is to R1. So it's a balanced Wheatstone bridge. Then this middle resistor can be ignored altogether. So it is equivalent to something like this. From A, there are two resistors R and R. The middle resistor was ignored, and continuing, there are two more resistors R and R connected to B. That's all. R and R in series becomes 2R. Again, on the lower side also, R and R in series becomes 2R. 2R in parallel becomes R. Okay, that's the effective resistance of this network of resistors. Okay, is it clear to all of you? Any doubts in this question? It's like these two became R1 and R2. These two became R3 and R4. This one is R5. And since all were equal, R1, R2 is 1:1. R3, R4 ratio is also 1:1. Okay. Try this question. I think I made it very obvious. Anyway, never mind. Calculate the current flowing in the circuit. Answer will be in terms of V and R. Isha, any answer? Okay, see, you are given a network or you're given a circuit in which there's only one battery and a number of resistors. In any such circuit, if you want the current, it is V divided by effective resistance of that entire network. Fine. So you have to simplify that network first and find out its effective resistance. So How shall we start? Anugraha, you tell me. What steps did you take?
2R and 4R are in series with it's a Wheatstone bridge, so 2R and 4R are in series with R
Okay,
and QR.
you made use of that Wheatstone bridge. Fine. So yeah, this part of the network, there are 5 resistors, no series, no parallel, and directly by seeing you can tell it's a Wheatstone bridge. So basically, where is the Wheatstone bridge? It's between this point and this point. Fine. And the ratio of the resistances on the left side 2:1. Ratio of resistances on the right side 4:2 is also 2:1. So it's a balanced Wheatstone bridge. And since it's a balanced Wheatstone bridge, we can ignore this middle resistor. 2R, 4R in series becomes 6R. R and 2R in series becomes 3R. That 6R is now in parallel with this 3R. Let me redraw the circuit quickly. So we can now take it like this. A 6R resistance here and a 3R resistance like this. And now if you observe, the 6R and 3R are in parallel. Effectively, they become 6 into 3 by 6 plus 3, 18 by 9, that is 2 ohms or 2R. So 6R, 3R together become 2R. Then you will see, like if this whole thing is 2R, then this R, this 2R, and current flows through that combination. This 2R, all 3 are in series. If R, 2R and 2R are in series, effectively it becomes 5R. Okay, so the current becomes V divided by 5R. Okay, we first simplified the Wheatstone bridge. There was another R here. We saw that it was a balanced Wheatstone bridge, so we ignored that middle resistor. Wheatstone bridge was connected between those two orange dots. The effective resistance of that Wheatstone bridge became 2R. Okay, so between those orange dots, there is a 2R, and there are another 2R and R in the circuit. So total resistance is 5R. Isha, any doubt in this?
No, sir.
Okay. Fine. Let us now discuss what to do if the Wheatstone bridge, okay, if there are 5 resistors, no 2 in parallel, no 2 in series, and it's not even balanced. Just a moment, I'll clear all this. Okay, suppose you are given a network like this, 5 resistors, obviously, and you have to find out the effective resistance. First, you will check whether it is balanced or not. If it is balanced, you know what to do. Any idea what to do if it's not balanced? Some of you may have learnt already. Okay.
Sir, Kirchhoff's voltage law.
You will use KCL, KVL. So suppose the ratio R1 by R2 is not equal to R3 by R4. So you can't do any simplification. Then there is a proper elaborate method to find out the effective resistance of any network, not just this one, not just an unbalanced Wheatstone bridge. Even if you are given a very complicated or a very simple network also, there is one sure shot method which will always tell you the resistance. Okay. Why don't we always use it then? Because it's a slightly lengthy method. Right? So yeah, We have to find out the effective resistance of this network, no? So what we'll do is we'll assume a battery is connected. We'll find out how much current flows through it because of that battery. Then we will divide them. We know V is equal to IR, so R should be V divided by I. So we'll assume there is a V connected. We'll find out how much current I flows. We'll divide them, we'll get R. Okay, that's the idea. So assume a battery is connected like this. They need not give you the battery in the circuit. But if you want to find out effective resistance, you can always do this. Assume a battery is connected, and due to that battery, assume a current I flows in this network. Then the effective resistance should be V divided by I. So now we assumed V, we assumed I, then is the answer V by I? No. Okay. We assume V. Let's assume V is known to us. We have to find out I. Okay. And when you do that, obviously you'll get I in terms of V and R1, R2, R3, R4, R5. You get current in terms of voltage and the resistors. And then you bring it and put it here in this denominator, the V part will get cancelled. You'll get effective resistance only in terms of R1, R2, R3, R4, and R5. Okay, that's the idea. How to implement that? Okay. A current I flows into this junction. Then it has two paths along which it can split. So assume the current in this branch is I1. Tell me, if a current I is entering and I1 deviates to one side, how much is the remaining current? Incoming current is I. Out of that, one part I1 goes to one side. How much current remains?
I minus I1.
I minus I1. So you can call this I2 and solve equations, not an issue. But we are solving some equations here itself. We are applying the junction rule. Inflow is I, one outflow is I1, then the other outflow should be the remaining current I minus I1. That goes through the resistance R2. Okay. The current I1 continues and moves to this junction. The current I minus I1 continues and moves to this junction. Now from I1, some may go this way and some may go this way. From I minus I1, some will deviate this way, some will go this way. And these two, which are like this will come here, may go like this, may go like that. So don't take currents one by one like this. Fine. Assume or imagine the final currents in these branches. See, like in this R5, there may be some current going this way, some current going this way, right? But ultimately, there will be one effective current flowing through it. Imagine that effective current. So let's say the current in R5 is effectively downwards, I2. Then see at this junction, I1 was coming in and I2 deviated this way. Then how much will go the other way? I1 minus I2 will go the other way. Okay. And at this junction, the lower one, I minus I1 was coming in from this side. I2 is coming in through the other branch. Then the total current here will be I minus I1 plus I2. I2 will get added. And that is what flows through R4. And all these currents, not all these currents, this one and this one, they finally combine and what comes out is I itself. If you want, you can check. I1 minus I2 flowing through R3. I minus I1 plus I2 flowing through R4. If you add those two, you will get I itself. So finally, the current coming out from the right side will be the total current I. Okay, now what is our aim? Our aim is to express I in terms of V and the resistors. Okay. V is known, resistors are known. We have to get an equation for I. Now, there is no loop which has only the current I flowing in it. So you will have to take loops with other currents and solve equations. One loop you will take is this, maybe start from here and go clockwise. Another loop you will take is this, maybe start from here and go clockwise. It's your wish. Where you start from, which way you move is your wish. Tell me, can you use this as the third loop? If you take those two as the first and second loops, can we use this one as the third loop?
No, sir.
We had discussed this a few classes back also. This yellow one that I have drawn is a combination of those two green ones, right? So if you write an equation for this third loop also that I have shown in yellow, it will just be the sum of the first two equations that you write, first two KVL equations that you write. And also, how many other equations you write for these loops, you will never involve V in that equation. Okay, that won't help you find out the effective current because, sorry, effective resistance. To get effective resistance, we need current in terms of V such that V gets cancelled and you will be left only with the resistances. Okay, so there's no point taking this loop at all. The third loop you take will be this one. Maybe the outermost loop like this. You may even take this path, not an issue. Okay, so for the first loop, you will get one equation. Second loop, you will get one equation. Third one, you can take the yellow one or the blue one, that will give you the third equation. And what will these equations be in terms of? You will get these equations will be in terms of I, I1, I2. Of course, the resistors will all be involved, R1, R2, R3, R4, R5, the resistances, and the battery V, EMF V. All these will be there in these three equations. Now, what are the known values in this? We know the resistances. We don't know effective resistance, but we know individual resistances. And we know the voltage. I mean, we assumed it as V. So V is known to us. The unknowns are I, I1, I2. Three unknowns will be there. You will have three equations. You can solve and get I from it. Once you get I, use this equation to get the effective resistance. Okay, so very lengthy procedure. But if the Wheatstone bridge is unbalanced, that is what you will have to do. You need to take the loops carefully. First, you need to distribute the currents carefully. Then write the KVL for each loop carefully. Then you will have three equations to solve. Care has to be taken at every step. Even if one minus is missed or one or two is missed, the answer will be wrong. And the same thing with capacitors also. If there is a Wheatstone bridge of capacitors unbalanced, then you will have to assume a battery is connected. Here, to find effective resistance, we write currents. In case of effective capacitance, you distribute charges. You can assume the upper capacitor gets a charge Q1, lower one gets Q2. Similarly, you will distribute charges. Okay, let us solve problems like that. First with resistors. Two ohm, 1 ohm. And on the right side, you have 1 ohm and 2 ohm. Calculate the effective resistance. Clearly, this is not a balanced Wheatstone bridge because the ratio on the left hand side is 2:1. Right hand side is 1:2. It's not balanced. So needless to say, you will have to assume there's a battery connected. Battery voltage is unknown, of course. If you want, you can assign a value, nothing wrong in that. Like you can take some 20 volts and then write the currents and then finally V by I, but keep it as V itself for now. So current I will be flowing here. Distribute currents I1, I minus I1. In the middle resistor, assume there's a downward current of I2. It's not compulsory. You can take it upward also, not an issue. But other current should be written accordingly. So I1 coming in, I2 went off this way. So I1 minus I2 continues to the right side. And here it gets added. So I minus I1 plus I2 goes in that 2 ohm resistor. Okay, solve this quickly, all of you. So do it this way only so that we all get a common equation. Start from here, move clockwise while writing the KVL equation. Second loop also start from here, move clockwise. Third one, start from here, move clockwise. Outermost loop we will take. Okay, Anugraha, tell me KVL for the first loop.
The green color loop, sir.
Green one, yeah.
Minus 2I1 minus I2 plus I minus I1 is equal to 0.
Minus 2I1 minus I2 plus I minus I1 is equal to 0. Correct. Isha, tell me KVL for the second loop.
Plus I2 minus of I1 minus I2
Correct.
plus 2 into I1 minus I2 plus I2.
Correct. I minus I1 plus I2. Okay, Shashank, third loop.
D equals I R F.
No. Tell me KVL equation for the third loop.
So what is the difference between the outer loop and the blue loop if we call it?
The blue loop does not involve the battery, no? Does not include the battery. The outermost loop includes the battery. The outermost loop considers this resistor, and this battery.
Minus 2I1
Minus 2I1.
plus I2 minus I1.
Okay, minus of I1 minus I2, you made it as I2 minus I1. Okay, I'll write it as it is, minus of I1 minus I2.
Plus V equals 0.
You're going from negative terminal to positive terminal, so plus V is equal to 0, right? So these are the three equations that you get. And your aim is now to express I in terms of V. So you have to remove I1 and I2. So from the first equation, you take I1, put it in the second equation. Then from the second equation, you take I2, put it in the third equation. Okay, let's see. We'll rewrite these equations first. First equation becomes like there's minus 2I1 and there is minus I1. So minus 3I1 plus I minus I2 is equal to 0. Second equation, I2 is there, minus of minus I2, that is plus I2, another plus 2I2. So totally 4I2 is there. And then minus I1 is there, minus 2I1 is there. So minus 3I1. And is there any I? There is a 2I is equal to 0. And in the third equation, minus 2I1 minus I1 is minus 3I1. Minus of minus is plus I2 plus V is equal to 0. Okay. Solving equations. I am very slow actually. Let us do it anyway. Our aim is to get I, so we should not eliminate I from the equations. The other terms have to be eliminated. Let us do that. Okay, we'll use the third equation. From third equation, what can we say? We can say I2 is equal to 3I1 minus V. We will put this in second and first equations. So the first equation now becomes minus 3I1 will stay as it is, plus I will stay as it is. Minus of I2 becomes minus 3I1 plus V is equal to 0. And the second equation becomes 4 times of this. So 12I1, 4I2 means 12I1 minus 4V minus 3I1 plus 2I is equal to 0. Okay. So we eliminated one of the unknowns. Now we have to remove I1 from these equations. So you can get I1 from maybe the second equation and put it in the first equation. From the second equation, you get 3I1 is equal to, okay, then there's 12 also. No? From the second equation, 12 minus 3, 9I1 is equal to 4V minus 2I. Okay. We'll have to put this in the first equation. So I1 is equal to 4V minus 2I whole divided by 9. Then the first equation becomes minus 3I1 minus 3I1. There is minus 6I1. So minus 6 into this 4V minus 2I by 9. What else is left? Plus I plus V is equal to 0. After this, I think you will be able to manage. So from this, you will get I in terms of V. And once you get I in terms of V, you write effective resistance is V divided by I. And the V term will get cancelled. You will be left with a number that is the effective resistance. Okay. You can finish it after this. Do it later and send me your answers. Now, what if the same was given? I got one answer as 7 by 5. Maybe, I don't know. We'll see. Okay, I'll solve it later and send you. And few days back, you asked the answer to one more question also. Did I send the answer to that question? Or you asked if a particular answer is correct or not?
About the inductors, sir.
Which one?
Inductors, the question that I sent. About using KVL, you responded for that question.
Okay, you're speaking too fast. About KVL?
The question
Okay,
based on
you got the answer in
KVL for
class.
inductors. No, sir, you sent it to me in WhatsApp only.
I sent one in WhatsApp, I remember, solution. You had asked one more question also. Oh, are all your doubts cleared?
Yes, sir.
Okay, no problem. Fine. Yeah, so if there is an unbalanced Wheatstone bridge, this is how you are supposed to do. It's a lengthy procedure. In exams, if you find such questions, no, you should do them at the end. Okay. Generally, I don't know if they told you in your coaching or not, never solve time-taking questions in the exam first. Okay, even see, this is easy only. We know how to do it, but still, if you attempt a question like this in the exam, in the 3-hour exams that they conduct, objective type, it will easily take up 10 to 15 minutes, and there's no guarantee of correct answer, because any one mistake in these equations, the answer is wrong. The answer will be wrong. Okay, so these are like lengthy time-taking questions, and there is a lot of risk also in this calculation. You should not attempt such questions before solving the other easier ones. Okay, I hope you all are aware of this, but I'll tell you once. If, like, suppose you are given a question paper, maths, physics, chemistry, all of you are preparing for okay, studying MPC only, fine. So maths, physics, chemistry will be there, 25 questions in each if it's a mains paper. You can start with whichever subject you are comfortable with. Let's say you started with mathematics, or let's say you followed this order itself, maths, physics, and chemistry. Start from the first question of mathematics, read the question. If you feel it is easy, solve it then and there, mark the answer. Go to the next question. If you feel like after reading the question, if you feel it's going to take time or you're not sure about a concept, leave it as it is. Or if you are sure but it is going to take time, mark for review. You will have that option also, no? So you see any question, you see the first question. If you can readily solve within 2-3 minutes, do it off. If it's going to take time, mark for review. If you have no idea, leave it altogether. Go to the second question. Okay. So effectively what you are doing is you are only solving if it is easy. I mean, if it is doable within 2 minutes or maximum 3 minutes. That's what you did to the first question. Same thing you will do to the second question. Same process will repeat till you go to the 90th question. Okay, including those optional questions I'm telling you. So out of, maths, physics, chemistry, all the easy questions should be done in the first round. This is the best way to approach, solve the question paper. Now you will do the questions which you had marked for review. Again, same order you can follow. Maths, the questions that you marked for review. Physics, the questions that you marked. Chemistry, the questions that you marked for review. Those you will do. Suppose you are still left with time, then you suppose you are very confident in physics, then you see those questions in physics about which you didn't have a thorough idea to solve. Maybe when you give it another thought, you get some idea, right? So in the last round, once the easy ones are, after solving the easy ones and after solving the questions that you marked for review, if you are still left with time, you should do those questions which you did not get an idea for in the first trial, whichever subject you are comfortable with. This way, this will be the best way to use your time, 3 hours in the exam. So see, with little practice only, you will be able to tell now whether a particular question is going to take time or not. So you should, like these general questions that you find in any book, those questions you should be very thorough. Any new questions that you find in the exam, whether it is mains or advanced, they will need this general basic knowledge anyway. Okay. So if you see a new question also, the steps to solve that new question will be similar to the steps you take to solve these basic questions. So if you are thorough with these basic questions, if you have solved them a number of times, number of questions, then you will quickly get some idea to approach those new questions also. And then you will be able to judge whether it is going to take time or not. So it's all based on how much you practice. Okay. Let us consider an unbalanced Wheatstone bridge of capacitors. I'll just tell you how to solve it. You solve it and send me the answer later. Okay, it's better, easier to draw a new circuit. And see, in this particular case, what I did was I took 2 ohm, 1 ohm on one side, 1 ohm, 2 ohm on the other side. After solving, you will realize, okay, if possible, you remember this one case. Not because it is 2 1 and 1 2. It's like R1, R2, and then here it is R2, R1, reverse. In that case, you will see after solving this problem, you can check if you want. The current we took here, we called it as I1, if I remember. I1. And the current here was I minus I1 plus I2. No, you will see that this current, I mean the current in this resistor and the current in this resistor are the same. And you will also see that current in this and current in this are same. Now, how is that a shortcut? It's a shortcut because if you are calling this current as I1, you can call this also as I1 while solving the problem. It will make you write equations faster and solve equations faster. But don't remember it. I mean, don't take it for granted. Okay. Solve this question thoroughly, get the value of I. Once you get I, you check the currents I1 and this one, I minus I1 plus I2. You will see that they'll be same. Now, if you want to check simply, you take voltage as some 20. You'll get I as a number. Then I1, I2, all numbers you will get. Then you will be able to verify. Okay. So if that ratio is just inverted, then the current flowing in that first branch goes through the fourth branch. Current in the second branch goes through the third branch. You can, but check it for yourself first. Don't take anything for granted. You know how to properly solve the problem, properly solve it. Then only you confirm whether that shortcut is always applicable or not. Okay. Suppose there is a network of capacitors like this. Unbalanced. If it is balanced, you will do the same thing that you did to resistors. Okay. If it is unbalanced, what to do? Assume it is connected to a battery. Some voltage, you can assign a number or a voltage V itself. Capacitances will be known, C1, C2, C3, C4 and C5. Now, how do you find out effective capacitance? For effective resistance, we are using V is equal to IR. For effective capacitance, we will use Q is equal to CV. So C effective will be total charge flown through the battery divided by V. Now, here we used R is equal to V by I. We expressed I in terms of V. To find effective capacitance, you have to express charge in terms of V. Okay. Of course, the other capacitance C1, C2, C3, C4, C5 will be there. Okay. And V will also be there. Okay. Now the battery is connected to two plates on the left side. Let's say this plate gets a charge Q1. This gets a charge Q2. If one plate is getting Q1, the lower plate is getting Q2, what is the total charge supplied by the battery? Is it only Q1, only Q2? Is it Q1 plus Q2? Is it Q1 minus Q2? What is the charge supplied by the battery? Assume all capacitors were neutral initially, uncharged. Now these two plates got Q1 and Q2, then how much charge was supplied by the battery? Supplied means pulled from one side and put on the other side.
Q1 plus Q2.
Q1 plus Q2. Both those plates are getting charged through the battery only, no? It will be Q1 plus Q2. So that is what is our target now. We have to find out Q1 plus Q2 in terms of V. Okay. So that's one equation. Q is Q1 plus Q2. And if that is Q1, this will be minus Q1. This will be minus Q2. There's another capacitor here. Assume it gets a charge Q3. Another unknown we are introducing. Then this will be minus Q3. If this is minus Q1, this is Q3. This isolated region you see, isolated regions must be neutral. So minus Q1, Q3, this becomes Q1 minus Q3, such that the isolated region is neutral. Same on the lower side. Minus Q3 minus Q2. So this becomes Q3 plus Q2, such that this isolated region is on the whole neutral. And then the other plate charges you can write Q3 minus Q1. Here it will be minus Q3 minus Q2. So that the total charge on this side, if you add them, it will be minus Q1 minus Q2. Makes sense. Total charge on this side was plus Q1 plus Q2. Then on that side should be minus Q1 minus Q2. Whatever charge battery takes on one side, it releases on the other side. So this is how you first distribute the charges. Now apply KVL. Same thing, same procedure. One loop here, one like this, and then the outermost one. You'll get the value, like with three equations, you can get Q1, Q2, Q3. all three charges in terms of V you can find out. Once you know Q1, Q2, Q3 in terms of V, you can tell Q in terms of V, which is Q1 plus Q2, and then divide them, you'll get the effective capacitance. So I'll give you one problem, solve it. Answer I'll send you tomorrow. You can verify whether your answer is correct or not. How much shall we take? Simple capacitance values only we'll take. Okay, same as those resistors. 2 microfarad, 1 microfarad, 1 microfarad, 2 microfarad, middle one, 1 microfarad. Find out the effective capacitance of this network. Okay, so do this by tomorrow itself. Your next class will be tomorrow. Exact timing I'll inform tomorrow itself. Maybe 7 or 7:30 it will start.